Okay, today we're going to be talking about triple integrals using spherical coordinates. This video may look a little different than all my other lecture videos because I had a technical issue with my camera in my last class, so I'm sitting here doing this video without a classroom full of students. It's just me, so if it appears that I'm not talking to the class, that's what's going on. Okay, so spherical coordinates. We already know that when we're looking at triple integrals, we are usually trying to do a triple integral over some region, let's say E, of some function of x, y, and z with respect to volume. And we've seen there is one way we can do these without using Cartesian coordinates, and that's to convert this to what we call cylindrical coordinates. And in that, what we do is we replace x, or we substitute x as r cosine theta, we let y be r sine theta, and we let z just remain z. And when we do that, this new integral gets transformed over to a new triple integral, and our region is the same region, right, but it's just represented with a different coordinate system. So I'll just call this S. And now we change x to r cosine theta, y to r sine theta. Z will remain z. And then very important, because we're making this conversion, we have to put r, and then it's going to be something like dz, dr, d theta. And the order here may change, but we have to insert that r because of the conversion. Today, what we're going to do is a new type of coordinate system, spherical coordinates, and the conversion there is going to be different than this conversion. All right, so let's talk about not only what that conversion is, but let's talk about the spherical coordinate system in general first. So for spherical coordinates, if we're going to convert from Cartesian to spherical, we're going to let x be replaced with rho cosine theta sine phi. Now, some people pronounce this phi, some people pronounce it phi. You might hear me saying both. Rho is like r, like the radius. So this is like we had r cosine theta back for cylindrical. Well, for spherical, it's going to be, we use rho instead of r. Rho cosine theta sine phi. Y is going to be rho sine theta sine phi. Z is going to be equal to rho cosine phi. And then we have an identity here that phi squared equals x squared plus y squared plus z squared. So what does this coordinate system look like? Let me get back to my initial settings here. All right, so imagine that you have the XYZ plane, or sorry, the XYZ three-dimensional space. And imagine that you are, standing at the origin and you're looking straight up the z-axis. And you're pointing, you're orienting yourself where you're not only looking up the z, but you're kind of facing, if you look straight down, you'll be facing the x-axis. So here's the x-axis, here's the y-axis, here's the z-axis. So you're looking straight up. And then we want to get to some point that's out in three-dimensional space. So I'm looking up, here's the x-axis. I'm going to rotate my head down. The angle that I make between myself and the z-axis, that's going to be phi. So I start to rotate out, and you can hopefully see, if I rotate this, I am, I'm kind of parallel to the x-axis here. So I rotate out a certain angle, okay, from the z-axis. That's going to be phi. And then, once I've rotated out, I'm trying to get to some point, I'm going to now, here's the x-axis down here, I'm going to rotate myself this way at some angle, and that angle is going to be theta. So let me rotate this. So notice that what's going to happen, I'm going to start swinging out this way. Okay, that angle here between the x-axis and the ground there is going to be theta. And then rho is how far I go out. So rho is the distance to that point. So I can decrease this. Let me try and zoom in, see if you can see this a little better. It might be a little bit easier to see there. Come at it from this side. So there's my phi changing, and then there's my theta changing. So if you can imagine right now, if I just take this point, okay, so remember rho is the distance from the origin to the point. If I just take this point and I start letting theta change and make theta go from 0 to 2 pi, then what's going to happen is I'm going to swing all the way around. Okay, I'm going to swing all the way around. Are you subbing? Okay. All right, I've got to stop this video. Okay, sorry, that video is going to look weird that it just cuts to this, but I got kicked out of that classroom. All right, so back to what I was saying here. If we rotate this all the way around, right, if I let theta vary, I'm going to swing all the way around. Let me zoom out a little bit. So you can see this point is going to come all the way around if I let theta go from 0 to 2 pi. And then if I change my angle phi just a little bit, so I rotate that point down a little bit more and swing my theta all the way around, and then just continue to do this, okay, let phi come down more, and even I can let phi go down below the xy plane and swing around. What I'm going to get in the end, all those points will form a sphere. So this might make a little more sense here. So notice if I change phi, I'm going to just move up to some point on the sphere, change phi, going to be up here some point on the sphere. And then if I change theta, it's going to swing me around the sphere. So all those points will create a sphere, which is why they call these spherical coordinates. So we do have some restrictions. The theta has to be between 0 and 2 pi. So when you're pointing, initially you're up. Phi can come down, or phi can go between 0 and all the way down, straight down, which would be pi. So phi is between 0 and pi. That's this. And theta, which is this angle, can go between 0 and 2 pi. So you can do a full rotation there. And then rho can be, of course, greater than or equal to 0. That's the radius of the sphere. All right, now, if those are the coordinates, then here are our conversions. If we want to go from Cartesian over to spherical coordinates, it's a pretty complicated conversion. There's your x, your y, and your z conversion. So just remember that when you go to spherical, that's your replacement. See, with cylindrical, we just did r cosine theta, r sine theta for x and y respectively, and z just stayed z. But for spherical, we had those. Now, those look like it might make it more complicated, but it turns out that a lot of these problems can become much easier by going to this coordinate system. Now, here's another example of a spherical region. So let me see if I can kind of show you this. I'm going to show it to you from the back side. So what we have here is I've taken my phi and I have restricted it between two constants. And I can use, let me see, hold on. I have it written down here. C and D, alpha, beta. Okay. So if I restrict my phi between two constants C and D, my theta between alpha and beta, and my rho between A and B. So let me explain that with this picture. Now we're looking at this kind of from the side. So what I've done is I've said, all right, look, I'm going to start pointing out up the z-axis. This is going to be phi. What I want is to restrict my phi between two constants. So let's say that's C, and then I can let phi be anything between C and all the way down to D. So that gives me all of this swing of angle here. But my theta is between alpha and beta, so my rotation, once I swing down, I have to start rotating around like this. If I restrict my theta between alpha and beta, then you can see this would be alpha, and then swinging through here would be to beta. So I'm allowed to get phi between C and D, phi, between C and D, and then theta is between alpha and beta. And then I let my rho be between A and B. So rho is how far out I walk. So if I'm here, I can swing down, I can swing anywhere in here, and I can walk out only between A and B. So this would be A. So the distance from the origin to any of these points on this little surface here is A. And then anything on that outer edge would be a distance of B, and it's everything in between. So what you get is this weird-looking solid shape, three-dimensional solid, which is really like a spherical rectangle. All your variables are stuck between constants. Now I can adjust this, which I will, just to show you some different variations. Let me make this a little smaller so I can see what I'm doing. How about I let my radius go from the origin out Okay, here's another region. Bring it up a little bit there. And let me just swing this around so I can see what I'm doing. Okay, what I've done here is I've restricted in spherical coordinates. I've drawn a ball, a solid ball, but I'm just looking at the first octant of that ball. And let's say it has a radius of, let me change the radius here to about, let's make it 2. So, close enough, 2. All right, there we go. So there's that. That's a solid ball, but I'm just looking at it in the first octant. So let's talk about my restrictions. If I wanted to draw that, my restrictions would be, let's see, so phi is the angle from here down to the x-axis, which would be 0, right, all the way to, what, a quarter rotation, so that's pi over 2. So my phi is between 0 and pi over 2. And let me just double check that I'm recording right now. I don't want to go through all this. I kind of got scattered there when I had to evacuate that room real quick. All right, I'm good. So phi is between 0 and pi over 2. And then my theta is the angle on the ground here. And again, I am only in the first octant. So if I look at it from the top, I can see the angle. This is the x-axis. I'm swinging over towards the y-axis. So that, again, is a quarter rotation. That's going to be pi over 2. So theta is between 0 and pi over 2. And then finally, rho is the radius. Excuse me. Excuse me. And it's all the points from the origin out to 2. So it's everything in between. So my rho is bounded between 0 and 2. So that's what that region would look like. Now let's just see what would happen. What if I change it so that my rho actually only goes from, instead of 0 to 2, how about 1 to 2? So I'm only allowed to include points that are distance of between 1 and 2 from the origin. So I would have, let me change this to about 1. See how close I am to 1 here. Pretty close, close enough. So look what happened here. It's like we carved out this region inside, right? So it's like we scooped out everything that was, we scooped out a ball, a portion of a ball in the first octant, right, that had a radius of 1. So that's what these restrictions on phi, theta, and rho would give us that spherical region. So you can see this region is very different than, it's a lot different than a cylindrical region is, and it's different than a Cartesian. I mean, in terms of it's easier to define this. It's very easy to define that region in spherical compared to, imagine trying to define that in Cartesian or cylindrical. It would be much more challenging. So whenever we have regions like this that we're trying to integrate over, it's natural for us to want to switch to spherical. All right, now let's talk about the actual setup of the integral. So if you have a region E, and you have these restrictions on theta, phi, and rho, then our triple integral will turn into, okay, so this is our conversion. We're going to go from alpha to beta, and I made it too big. Let's go 150. Okay, it'll go from alpha to beta, and that'll be our restriction on theta. And then it'll go from C to D, and that'll be our restriction on phi. And it'll go from A to B, and that'll be our restriction on rho. And then all you do is you go in the function, you replace the x with, remember what I said, we have to turn x into something ugly. Here it is. All x's will be replaced with this. All y's replaced with this. All z's replaced with this. And then we have this very important rho squared sine phi. That is kind of like, remember when we did polar, and even in cylindrical, we always had to throw an r in there. Well, anytime you convert to spherical, you're going to have to throw a rho squared sine phi. Always remember to put that in when you go to spherical. In the next section, 12.8, I'll actually talk about where that comes from. All right, so I think it's time for us to do an example. So let's do the triple integral of e to the square root of x squared plus y squared plus z squared with respect to volume, where e is the region in the first octant between the spheres of radius 4 and 9. So what I have here is I'm looking in the first octant. Only in the first octant. I have a sphere of radius 4. So let's say here's 4, here's 4. And we know we have a sphere. So it's going to be, that's the first, just the first octant portion of that sphere. And then we have another sphere, which has a radius of 9. Up here at 9. So it's going to go like this, like that. And it's the region between the two. So this is exactly, well, not exactly, but very close to this picture I showed you a second ago, right? Except in the picture I showed you, the radius that we had was 1 and 2. Here it's 4 and 9. So it's this picture with that scooped out piece. It's the stuff in between. So we should be able to define that region pretty easily in spherical coordinates. So in spherical, we're going to have that phi is between 0 and pi over 2. That theta is between 0 and pi over 2 also. And this time rho is stuck between 4 and 9. And now what we do is we try and set up this triple integral with spherical. So I look at this triple integral over E, and now I know it's going to be triple integral. I know I'm going to have these restrictions. I'll worry about the order in a second. E to the square root of x squared plus y squared plus z squared. Well, remember earlier when I had this note up here that there was a nice equation right here. Rho squared is x squared plus y squared plus z squared. So if I take the square root on both sides, right? This inside piece right here is x squared plus y squared plus, x squared plus y squared plus z squared. That is rho squared. Take the square root, you just get rho. So when I convert that to spherical, that's just going to be e to the rho. And then because I'm switching to spherical, I have to put in that special thing, which is rho squared sine phi. And then my order of integration doesn't matter because these are all constants. So I'll go d rho, d phi, d theta. And then my limits of integration here, 0 to pi over 2. It's my restriction on theta. Phi, 0 to pi over 2 again. And then rho goes from 4 to 9. And that's the integral that I need to do? All right, so if I was going to do this, I'd first integrate with respect to rho.